Hi everyone, welcome to Lecture 4 of our course Communication Networks for Power Systems. Today we'll talk about Supervisory Control Data Acquisition System, also known as SCADA. SCADA system creates the foundation of any real-time distributed control system. Essentially, it consists of a host computer which receives information from various sensors within the system through a communication network. So in the very general case, we can show it as the communication cloud. So here you have sensors and you have actuators. These sensors would generate data, and the data through the communication network is sent to the host computer, which will then process that information, generates commands and set points, and then sends them to individual actuators through the communication network. We often liken the SCADA system to the human body, where your sensors are like your eyes and ears or other sensory system that will collect information from the environment in which you're located. Your hands and muscles are essentially your actuators that would receive information from your brain and then take actions. The host computer obviously would be your brain that receives information from your sensory system and processes it and generates commands for your muscles. And of course, the communication system is similar to the nervous system that has the role of connecting our sensory systems and muscles to the brain. There are a lot of benefits associated with the SCADA system. First and foremost, it allows us to perform distributed control when we have a lot of devices out in the field that need to communicate with a central computer. It also allows us to automate our systems, basically taking the human out of the loop. This, of course, makes the response time of the systems a lot faster. And with the way modern SCADA systems are designed, a system expansion is relatively easy, meaning that it offers the condition of scalability. Let's talk about the main elements of the SCADA system. The two important elements are the RTU and the PLC. RTU is the remote terminal unit, also known as the remote telemetry unit. This is an electronic device that provides an interface between the physical equipment and the SCADA system. The physical equipment can be a generator, a motor, a contactor, a breaker, a pump. There are so many examples depending on the domain in which the SCADA system is used. In order for that physical component to be able to send information to the host computer or receive information from the host computer, it would need some sort of an interface between itself and the communication network. The role of this interface is on RTU. We also have the programmable logic controller PLC, which is basically an industrial computer and directly connects to the physical equipment, can extract measurement data from that equipment and send it to the host computer through the communication network of the SCADA system, or, for example, can receive commands and set points from the SCADA system and then implement it locally at the equipment level. PLCs were originally developed in the auto industry. The goal was to simplify the design as well as troubleshooting, and also provide means for scalability and upgradability when they wanted to build newer models. Both RTUs and PLCs have to be utility grade, which means they should be able to operate within a harsh working environment, such as a substation or a distribution feeder, where you might be exposed to electromagnetic interference or various types of transients. In addition to providing an interface between a physical component and the SCADA system, an RTU can perform protocol conversion. This may be necessary if you have a SCADA system which is designed based on a newer IP-based protocol such as IEC 6870, and it's connected to let's say a legacy device, some sort of a device. which is generating data based on an older communication protocol like a serial Modbus, for example. In a situation like that, if the device talks Modbus and the entire SCADA system is operating based on, let's say as an example, 6870, then the two cannot communicate with one another directly unless some entity in the middle can translate from one protocol to another, and that would be the job of the RTU. So it would receive information using Modbus protocol, translates it into IEC 6870, and then puts it in the SCADA system. And when it receives a message from the host computer, which is based on the protocol IEC 6870, it would translate it back to Modbus, which is understandable for that physical component. Now these RTUs are typically polled by the host computer in order to report their data. Polling can be classified as balanced or unbalanced depending on which entity has the right to initiate it. In unbalanced polling, the entity that can initiate communication is always the host computer. So the host computer sends a polling message to the RTU, to which the RTU will respond with its data. If the RTU has something important to report, it cannot initiate the communication. It would have to wait for the polling signal from the host computer to then be able to respond to it. Opposite of that is the balanced approach, in which both parties can initiate communication. The host computer can, and the RTU, if it has something important to report, it can send it to the host computer without waiting for permission. From another perspective, polling can be classified as cyclic or RBE. Cyclic is when you have a series of RTUs that have measurements to report. This could be voltage, current, active power, reactive power, can be anything. And the host computer would poll them in a sequence, one at a time. So first it polls first RTU number 1, and then RTU number 2, which will respond with its data, RTU number 3, and so on. As you can imagine, if you have a small number of RTUs in the system, this is an efficient approach because it's not going to take a long time for one full cycle of polling to finish. However, if you have a large number of RTUs, this is not the best approach, because if one of the RTUs has suddenly something very important to report to the host computer, it cannot do that until it's its turn again. Now, if you have a large number of RTUs, the full cycle might take a long time to finish, and by that time, you have lost access to that critical information. So some critical information might be overwhelmed by just the sheer volume of ordinary data that needs to be transmitted from all the RTUs to the host computer. Another approach to kind of conserve on the bandwidth a little is the RBE, report by exception, in which the host computer would poll the RTUs, again in a cyclic fashion. If the RTU has nothing to report, it would respond with an empty acknowledgement. If it has some new value to report, it would add it as a payload to the message and sends it back to the computer. The empty acknowledgement has the benefit of notifying the host computer of the status, like on-off status of different RTUs. So if it polls an RTU and does not receive an empty acknowledgement, it realizes that that RTU is off or is having issues for some reason. At the same time, because it's an empty acknowledgement, it's not going to take a lot of resources in terms of the system bandwidth. Now, if you want to address different scenarios, you can combine the balanced versus unbalanced communication, or rather polling scheme, with the cyclic or RBE polling scheme. So for example, if you have devices that imagine there's an RTU that is interfaced with a breaker. A breaker does not change status all the time. If it has a status of on, it might stay in that situation for a long period of time before it's switched off, which again might be in the off position for a long period of time. So it wouldn't make a lot of sense to keep polling that device. Instead, what you can do is you can ask the device to report a change in status to you. So this means that you would have to have a balanced approach, meaning that the RTU can initiate communication if it has something new to report, and you can combine a balanced approach with the RPE polling approach. Let's take a look at the PLC, the Programmable Logic Controller. As I mentioned earlier, this is an industrial computer that consists of a central processing unit as well as a memory, and it has an interface with the RTU, which itself is the interface of the device to the rest of the communication network. The PLC can receive digital inputs and analog inputs, and can send digital outputs or analog outputs. Imagine if it's interfaced with a breaker, for example, the status of the breaker, whether it's on or off, it would be a digital input to the PLC, which would then be reported to the SCADA system through the RTU. So that status S would be reported to this to the PLC, stored in its memory, and then pushed into the outgoing terminal through the RTU to the rest of the system. Likewise with analog inputs, for example, if there is a measurement of a voltage, a current, a position, anything like that. At the same time, if there are messages that are being sent to the PLC from the, let's say, from the host computer here, those messages will come to the RTU pushes it to the PLC, and the PLC, based on what device this information or this data is intended for, it will pass it to that data. For example, it could be an on-off command, a digital output to switch on a device or switch off a device, or turn on an alarm or anything like that. Or it could be an analog output. For example, imagine there is a set point that you want to send to a generator, saying that it needs to generate so many megawatts. So this would be a signal that will come from the host computer through the RTU, will go to the PLC, and the PLC applies it to that particular generator. So these inputs would be essentially the sensing capability for the PLC, and the outputs are the actuation capabilities of the PLC. You also notice here in this diagram that for analog input and output, I'm using the notation of 4 to 20 milliamp live 0. This means that let's say your analog output changes between 0 volts and 5 volts. You code 0 volts as 4 milliamps and 5 volts as 20 milliamps. You do this intentionally because if 0 volts is coded as 0 milliamps, every time you get 0 milliamps, you would assume that everything is fine, and this is just indicating a command of 0 volts, for instance. However, it is possible that you have an issue in the system. For example, one of the conductors break. If the conductor breaks, you're not going to have any current flowing through that conductor, so you will have 0 milliamps, which is an indication of a problem in the circuit. However, you would be interpreting that as 0 volts. So in order to distinguish between the two, we say if the analog value changes from 0 to 5 volts, as an example, it doesn't have to be these values, but just as an example, I code this as 4 milliamps and this as 20 milliamps. So if I read 4 milliamps, I know that the system is operational, the circuit is connected and operational because I have current flowing through it. It's 4 milliamps of current, which means it's 0 volts. And if I have 0 milliamps, that's an indication of error. So that tells me that perhaps I have a disconnect somewhere in the system, and I can tend to it. So these are known as 4 to 20 milliamp live 0. Traditionally, in SCADA systems, all the connections were hardwired. So if you had devices that would have to connect to multiple other devices, between each pair there would have to be a physical wire, physical conductor that would connect the two. As you can imagine, this would make the design complicated. More importantly, the troubleshooting would be very complicated. So if, for example, you would notice an inaccurate signal somewhere, it would be very, very difficult to go back and figure out what wire might be having issues. In modern SCADA systems, we have addressed this by introducing the local area network. So here, instead of having physical wires between every pair of devices that need to communicate with one another, we just have a local area network. All the devices would put their data there, and this data is addressed to the particular destination. Everybody would see that data, but only the device whose address is included in the destination address would actually get the data and use it. So in this case, for example, could be the host computer. This significantly reduces the number and length of wiring and simplifies troubleshooting in the system. Okay, let's talk about some functionalities of the SCADA system. One of the important ones is data acquisition, which is part of the name. SCADA stands for Supervisory Control and Data Acquisition. So here you can receive status data, which is, for example, a status of an alarm, a status of a breaker, or you can have measurement data, continuous data, for instance, voltages, currents, active power, reactive power. There are also ways to specifically measure energy values. So instead of looking at the actual value of energy or power, for instance, you would generate pulses. Imagine in this example, if one pulse is representative of half a megawatt hour of energy, then instead of receiving the actual value in megawatt hours, you receive a number of pulses, and then you translate this number of pulses into the actual energy value. Regardless of how you do this, the SCADA system allows us to capture data from all the different sensors we have distributed in the field. It allows us to monitor different variables of interest. There are various possibilities for this. You can do status monitoring, which is you look at a particular variable of interest and you observe how it changes with respect to its previous values. This is helpful and beneficial if, for example, the variable is not supposed to go through significant changes. So if it does, it's an indication to you that something non-ideal is happening in the system. You can do limit value monitoring, where you have certain dead bands for various variables, and you compare the value against the dead bands to make sure that those thresholds have not been passed. SCADA systems can timestamp data, and this is especially important when you want to look at the sequence of events, especially in post-mortem analysis after a significant disturbance in the grid. You always want to go back and try to do a root cause analysis and see what caused this event and what sequence of disturbances led to, for example, an outage. By having a timestamp of individual data points, you can always go back and reconstruct the sequence of events. We can do trend monitoring. This is when you have a particular variable that is going through unusual variations. It could be like a variation in the wrong direction, something you don't expect, or very quick changes that is not natural for that variable. As an example, imagine you have a tap changer. A tap changer for a transformer doesn't really change position very often. So if you all of a sudden are reading this tap position that is becoming positive and negative all the time and going through fast changes, the trend monitoring module of the SCADA system can indicate that as an error. It also allows us to have more of a general situational awareness by adding quality attributes to different data points. These are some examples here. For example, a quality attribute could be updated or not updated. If you receive a voltage measurement that has a quality attribute that, hey, this value has not been updated for a long period of time, that perhaps is an indication that something might not be right with that voltage meter, so you perhaps should not trust that measurement. Another attribute could be manual, which is a binary attribute, whether the data has been manually entered or not. Manually means that, for example, a human operator has entered the data manually as opposed to the value being directly measured by a measurement device. Another attribute is calculated. Sometimes you don't measure a variable directly, but then you calculate it using the information that you have. For example, imagine you have a system whose node voltages you know and the impedances you know. So the voltages are something that you measure directly, but then you can calculate the currents with the knowledge of the voltages and the impedances. So that basically indicates to you that this value that you have received, has it been directly measured or has it been indirectly calculated? There are other attributes. For example, if a particular data point has been blocked for whatever reason that the operator deems necessary, or for example, if it's out of range based on a particular upper and lower threshold that you define, or perhaps going through values that are not normal based on the historical data. Imagine you have been measuring a particular node voltage for weeks and weeks, and all of a sudden you measure a value that is not close to what you have been measuring in the past. Now this value may not necessarily be wrong. For example, you may measure a voltage which is 1.02 per unit. There's nothing wrong with this voltage. In fact, it's quite possible that you get something slightly above 1 per unit. However, if historically in the past 6 months the value of that voltage has always been between 0.95 and 0.99, then all of a sudden the fact that you're measuring 1.02 is something abnormal, and this again can be indicated to you with a quality attribute. This is an example of comparing a particular measurement value against different deadbands. So as you can see in this hypothetical example, you can have a normal operation range. If it goes slightly above or below that, it would be a warning zone, and then you would have a range for excessive values, that if your measurement goes to either here or here, this would be a cause for sounding an alarm. You can see that if your measurement value, which in this case is this line, crosses one of the thresholds, an event is going to be generated. And no new event will be generated until another threshold is going to be crossed. So notice here that you go up and down, despite the fact that you go slightly above this threshold and slightly below this threshold, because you're not crossing other thresholds, no event is generated here or here. However, when you cross another threshold, which is this new guy, then there will be a new event generated. Control functionality is also another important aspect of the SCADA system, again being part of its name, supervisory control and data acquisition. This could be manually implemented by the human operator, or it could be automatic. A human operator can implement a manual individual device control. For example, if you want to turn on a device or turn off a device, or switch on or switch off a component. It could also be a control signal to a regulating equipment. For example, if you want a particular generator to be producing a certain amount of active power, reactive power, you can send that command. Or it could be a sequential control. This is a series of control actions that if a human operator activates it, all these actions will take place one after the other. For example, it could be, if I implement the sequential control, you would have to open that normally closed tie switch and close that normally open one, disconnect that load, and then increase the generation level of that generator by that much. This whole thing would be a sequence of control actions. The control can also be automatic. This is a situation in which a control action is triggered by a particular event or at a specific time. An event example could be, for example, an undervoltage situation. If all of a sudden the voltage at a particular node goes below a certain threshold, this might trigger a particular control for a transformer tap changer to increase the tap positions, raise the taps in order to increase the voltage. Another situation could be the control being triggered at a specific time. Some example of this for distribution systems are shunt capacitor banks that are switched on during peak load conditions in order to help with providing reactive power support. So you could have a time-based controller that whenever you get to the peak load hours, let's say 6 p.m., the capacitor is switched on and it remains on for 2 hours, let's say, and then it's switched off. The SCADA system also has the capability for data storage and analysis. As I mentioned earlier, this is quite important for sequence of event analysis, especially because all the data points are time-stamped. You can always go back and see what root causes led to a particular disturbance or a particular outage. What is known as the post-mortem review or post-mortem analysis. You can store this historical data, go back to it, not just for post-mortem analysis, but you can, do all sorts of statistical analysis using the historical data that you have, and the SCADA system gives you that opportunity. Now, the SCADA system is the backbone of the controller, which means that it's extremely critical for the integrity of the system that is trying to control. Because of this, we often introduce certain levels of redundancy into the design of the SCADA system. This could mean that, for example, your servers or your host computer consist of 2 units, one that is always online and one that is on standby. You can implement the same for your local area network or the communication front end. So you can have a network component that is online and another one which is standby and ready to jump in whenever necessary. As far as communication between the RTUs and the rest of the system are concerned, you could have high reliability designs. Consider this situation. If you have point-to-point connection, if there's anything wrong with that particular connection, you're going to lose that RTU. But by using more resilient schemes, for example, the loop configuration or the star configuration, if let's say this path is for whatever reason not available, this device can forward its information to this RTU, and this one would pass it to this RTU, and this RTU would send it to the host computer. So this way you have a certain level of redundancy. There are a lot of different communication media that can be used for the SCADA system. Like many other engineering applications, these would fall under the categories of copper, fiber, or wireless media. The options for copper are twisted pair, coax, or power line communication. Twisted pair is the cheapest option, but it has the lowest performance. Coax is more expensive, but it has better performance. Power line communication, and by the way, notice that power line communication also has acronyms of PLC, which is the same as a programmable logic controller, but these are completely different things. Power line communication is a technology in which you superimpose your data on top of your 60 Hertz component. So this is your power line that is, let's say, flowing a particular current signal at 60 Hertz. You add high frequency communication signals on top of this, and then it basically piggyback on the 60 Hertz component and goes from source to destination. PLC is attractive because the utility already owns the conductors, doesn't have to pay for additional equipment, doesn't have to pay for additional right-of-way. So you can just use the conductors that it owns and send information through it. There are some challenges, of course, in terms of performance, in terms of the transformers acting as a filter and filtering out the high frequency component of the superimpose data, and we're going to talk about that later on when we discuss power line communication in more detail. Another option is fiber optics. Fiber optics are very efficient, are expensive compared to copper. However, they offer resilience against cyber intrusion, because a hacker is not going to be able to tap into a fiber line as easy as they could with a copper line. So whenever cyber intrusion is a must, fiber would be a very good option. Of course, fiber offers much higher data rates than copper. It's immune to electromagnetic interference, so there's a lot of positives with that. And last but not the least, we have wireless, radio networks, satellite communication, cellular systems. The benefit of wireless systems is that you, again, don't have to pay for right of way. You can deploy the system with relatively lower cost because you don't have to deploy, fiber optics lines or copper cables. It does, however, or I should say could, however, introduce delays, especially, for example, using satellite communication. Nevertheless, it is an option that can be implemented for SCADA systems.